as David said, we're doing an experiment at TRIUMF, and one of the things that we might shed some light on is this antimatter asymmetry. And this is the sort of what David is working on. You start off with equal matter and antimatter, and then after the people run around with their colored cards and annihilate, there's this slight excess. And at this stage, you need a certain amount of so-called CP, charge parity violation, and it's also the same, it turns out, as time reversal in violation, like a lack of time reversal symmetry. And so I'm going to show you what we're going to measure, the neutron electric dipole moment. So I want to tell you what that is, why it's related to this, and how we're going to measure it. So first of all, I was trying to explain to my wife about the electric dipole moment, and I started in and she said, whoa, what's a dipole? So anyway, there's a dipole. As you might expect, it's something with two poles, right? And so you've got the magnetic dipole, which has a north pole and a south pole, or you could have an electric dipole. Now this you've probably seen. Electric dipole, you probably have two. Like if you take a party balloon and rub it on your hair, and you go like this, the hair sort of sticks out, and that's because the balloon's got one charge and your hair's got the other. So that's a little electric dipole right there. And these have certain properties, like the magnetic dipole will line up in a magnetic field. A compass needle is a magnetic dipole. It lines up in a magnetic field. An electric dipole lines up in an electric field. So if you have like a positive plate here and a negative plate there, you put the electric dipole in. The negative end is going to be attracted to the positive plate and the other way around. So that lines up with a magnetic field. And these two properties will let us look for this electric dipole moment. So there's what it actually, that's a dipole. This is the dipole moment. Okay, so how can a neutron have this electric moment? Because a neutron's neutral. It's a neutron. Actually, I probably have time for a short story. One time when we did experiments at Brookhaven on Long Island, we're going through the American border, and one of the graduate students who looked more like a rock musician in those days was trying to explain to the guard that he's working on this physics experiment. The guard said, "Oh, is that so? What's the charge on the neutron?" As if that would prove that he was a physicist. Anyway, the thing is that the neutron, although it's neutral, inside the neutron, as you saw in the earlier talks, there are positive and negative quarks. And so it's possible that that the charge centers aren't in exactly the same place. And if that's, so what you do to get the dipole moment is if you have plus q, minus q, separated by a distance, L, then the dipole moment is just the charge times the separation. And you see these numbers are really small. And the standard model is too small to see. The best experimental limit is around minus 10 to the minus 26. I mean, you know what these numbers mean, right? Like 1/10 would be 10 to the minus 1, because 10 has 1 0, right? 1/100th is 10 to the minus 2, because 100 has 2 zeros. So this is 1 over like 1 with 31 zeros and so on. But it can't be much bigger than this. And suppose it was 10 to the minus 26, right? And I want to blow up the neutron big enough that I can see the separation. Well, by the time the neutron got to be as big as the whole Earth, the separation would be only micrometers, like thinner than a piece of paper. So it's a small number, tricky to measure, but it would be nice. It would be nice if we could do it. Okay, so here's how it ties in to time reversal violation. You can see it quite clearly from these equations. However, you can also see it from the picture. So this is the neutron, that's the positive charge center and the negative charge center, and the arrow shows the direction of the spin. Okay, so and that's the direction given by the advance of a right-hand screw. So if the neutron's spinning like this, then it's up. If it's spinning like this, it's down. And so if you have the movie and you play the movie backwards, the neutron's spinning like this, you play it backwards, it's spinning down. But when you play the movie backwards, the charge is still in the same place, right? So it's not, it breaks time reversal symmetry. And that's the same thing that David would predict with his CP violation. So the same theory that might explain the baryogenesis would also predict a certain value for this EDM, and so we should measure it. Okay, so how you got to use some tricks. Okay, so here's an example of a gyroscope that's turning around. Okay, and the reason it does that is because it's trying to line up with the gravitational field. Like if that's it, right? It's going to want to go over and hit the floor, or it would really want to just go like this, right? It wants to line up with the gravitational field, but because it has angular momentum, it precesses. And it's the same thing with the neutron. The neutron has this magnetic moment. It has a magnetic moment for sure. We don't know about the electric, but it certainly has the magnetic moment. So if you put it in a magnetic field, it's going to precess around. And so what we do to measure it is this. You get the neutrons and you put them in a magnetic field, and they start precessing around. And then you put an electric field in there as well. And if there's no magnetic dipole moment, the electric field won't make any difference at all. But if there is, then when you change the direction of the electric field, you're going to change the precession frequency. And that's what these pictures are showing. When the electric field and the magnetic field are parallel, it speeds it up or it slows it down. And you know, generally you want a really weak magnetic field and a strong electric field, because you want to be able to see it. So the way you measure the frequency really accurately is by using something called a Ramsey resonance, and you notice the spelling, right? It's not my resonance. I wish it was. I could add a Nobel Prize to my resume. Anyway, so what you do is you get the particles in a magnetic field, and then you can calculate. You know the magnetic moment of the neutron. You can work out how fast it's precessing, and then you apply an external oscillating magnetic field, and you go through this series of spin flips. And if you hit the frequency right on, then the neutrons end up all pointing straight down. So you got them going. You go whoop, whoop, you do the Ramsey resonance drill, and then if you've got the frequency right on the button, they're all going to be down. And if not, you got to try again. No, but anyway, so actually it's not, you don't have to just keep trying. So what you do is you know pretty where this is, so you just do maybe some measurements on each side of the curve. That's the equation for the curve, so you can just do a fit and pick off the resonant frequency. So that's what we do there. Now, in order to do it, we put the neutrons in some kind of a bottle with a good coating on it, like diamond-like carbon or something. And then you can hold them long enough to do this measurement, which takes a few minutes probably, right? Maybe 3 to 5 minutes. So you got to hold them. And it's really hard to stop fast neutrons. That's why what I'm leading up to, of course, is why we have to have the ultra-cold neutrons. So a good thing for reflecting ultra-cold neutrons is nickel, but not for fast neutrons. So I looked up the interatomic space in nickel, and then you can also look up the size of a nickel nucleus. And so if you had the nucleus of nickel here, about the size of a golf ball, the nearest nucleus would be right out at 16th Avenue, like at Save-On Foods or something. So to a neutron that can't see the electric force, a fast neutron has to make a direct hit on the nucleus. So they just see like a nucleus here, another one a kilometer away. They just whistle right through. I mean, even a fairly good sized nickel plate, you're unlikely to get a fast neutron to even deflect. So what you have to do is cool the neutrons down. And so if you can get the neutrons down to something like 3 millikelvin, they're traveling 7 meters a second. A fast neutron, just for comparison, is going 50 million kilometers an hour. This is going about 25 kilometers an hour. You shoot one of these things up in the air, they'd only go up a couple of meters and they fall down again. So we slow them down, and this is an oversimplification. It's sort of a quantum mechanical thing. For each material, there's a speed below which they bounce off. And they usually just express it as an energy, and call it the Fermi potential. And you can look those up over 50 million kilometers an hour. Then they go into some heavy water, just room temperature heavy water. And then they bounce around there and get cool. Then they go into heavy water ice, frozen heavy water. And then finally, they bounce off some superfluid helium. Right now, we only have that we've got the target in place, which I showed some of the people where this area was when we were in the meson hall. And we have the cryostat, we have the room temperature D2O and the D2O ice, but we don't have the ultra cold part yet. That'll probably be next year or something. So actually, just to see that, like that's a schematic. This is what it looks like, or what some of it looks like. So what's happening is that the proton beam's coming in here, the tungsten target's down under that. This is the cryostat with the heavy water and heavy water ice, and eventually all this is going to be covered up, and somewhere down here will be the bottle for the ultra-cold neutrons for the EDM measurement. I think I have oh, this is working good. So this is, Rudiger made this. This shows the whole thing cycle. So watch here and you'll see neutrons are produced, they go along, they come up, we do a Ramsey resonance, we open the door, they go down here and get measured. Then we do it again, you see. They keep going over and over until you've got the EDM. 10 years, maybe. So anyway, this is what might happen. You see, here you have the upper limit of the EDM. What that means is that, like in this part here, the upper limit means that if it's higher than that, you would have seen it. Like we know that the EDM isn't 10 to the minus 24, or we would have seen it already. But this area is still possible. It does the beyond the standard model predictions in this region haven't been ruled out yet. And now this doesn't, so we want to go from here down to here. I mean, it's a bigger deal than it looks like. It's like, look at between here and here is a factor of 100, right? So we might get to something like 10 to the minus 27 in 5 or 10 years. And that would mean that any beyond the standard model prediction that falls up here would be ruled out. And better yet is you see one, actually measure one. But if you can't, then at least an upper limit helps a lot. So that would definitely bear on whether the model is right at what the CP violation that was used to predict the matter-antimatter asymmetry is also agrees with an actual measurement, so that's real support for the model. So we, like I say, maybe by 2017 or so, we might start getting a window on that.